let's get going. This is the first webinar, and it's time to coincide with the publication. There are now about 45 planners on the website for Year 7 and 8, and the rest of the curriculum will follow within the next 10 days or so, with a lot of checking going on in between, because it's a very kind of intricate job to get everything right, as you see, with such a kind of complicated framework to get so many things together and working coherently and all mapped across the 5 years has taken us a long time. But it all started really with the change to GCSE. As you know, there's more than 50%, actually 60% of the marks that are not for what students can just recall. They have to go beyond what they know, apply and analyze. And when it came out, we thought, well, maybe there's going to be a bit of a sea change in the way curricula get taught to reflect this, but there wasn't. So we put this metaphor out there because it seemed to us that it's very much like the way the universe is constructed. You can only see a small percentage of the matter. The rest is dark. We don't know what it is. And you can argue that the same is true of GCSE, that what's in the statements, the visible stuff, is actually only a percentage of what students need to be able to do. That stuff, the AO2 and AO3, hasn't been put into words. It's only there in the assessment section very briefly. So what do? That's really what Blueprint is about, is a framework to try and get students to the level that they can actually do those more difficult demands. What does it mean? Well, it doesn't mean just having textbooks and PowerPoints, which by their nature tend to focus very much on the statements on AO1. We need to go further than that and figure out what it is that students have to be able to do in addition to apply and analyze. A lot of that comes down to the depth of understanding of the ideas, which creates a problem because there's so much content that people don't have time to go into it in depth. That catch-22 we've solved, as you'll see, through big ideas and key concepts. The other part of it is using inquiry, integrating that sort of scientific thinking with the ideas, and knowing various strategies to help you recognize questions, to organize information, to interpret data. All of these things we think need to be taught and practiced many times for most students to get them. So the kind of curriculum we're envisaging that would do these more difficult steps is called an aligned curriculum. It's a fancy word, which just means design. It means knowing what it is you want students to be able to accomplish first, before you write the goals, before you write the assessments, before you plan the lessons. As you're probably aware, very often it's done the other way around. We have loads of lessons. They were designed for some previous incarnation or just happened to have, got organized into your file cabinet. And there isn't really a design there at all. It's more of a kind of hodgepodge of things cobbled together. Design means starting off with a very clear idea of what the outcome is, what the experience has to be for the user. And so that's where we started, to try and define what it is students have to be able to do. Then we work backwards and go, okay, what should the goals look like? What kind of assessment do they need? And what do those learning plans need to look like? And you'll see we've ended up with something which is a bit different. So essentially, we've given you a choice, right? The easy choice is just to teach the spec, just to use the textbooks and the schemes of work that many publishers have produced that are geared to that kind of specification approach. And it works very well for AO1, and obviously for students who are capable, they can figure out what to do with AO2 and AO3 as they've always done in the past. The problem is that a lot of the students are not going to do that. And that's why we need an aligned curriculum, one that actually teaches them what's involved in going further and deeper. There's a double benefit because that kind of aligned curriculum is much more likely to produce the desirable long-term outcomes than something where students are just being, force-fed content. So we hope that this path of an aligned curriculum, which is what Blueprint aims to be, is actually more compelling than sticking with what people have often had. But what is it based on? It's easy enough to say we want to do all of that, but there has to be a body of research that shows how to do that. This is what we've been presenting for the last couple of years, the idea of taking novices and turning them into experts. You can easily read about that or download things that we've produced before, and I will only just summarize in 2 slides what we're trying to say, which is that you can regard students, even GCSE students who are not very good at going beyond AO1, as novices. And the way that their mind organizes what they know is rather disorganized, like this book collection. They have lots of knowledge, but it's not easy to find what they need, and that's what's really crucial to solving problems. So contrast that with the expert. You have a different memory structure. It's organized, it's hierarchical, and what that means is it's easier to find what you need to solve the problem and connect all the information in the question with what you already know. This has all been researched from the 1960s, and of course there is a massive world out there where teaching or learning is based on a sort of expertise model. Think about chess, music, sports. We know what experts can do. We know what the steps are to get there from being a complete beginner. We've actually done that in other subjects like maths, which is very kind of clear hierarchical subject. So it's quite easy in those realms to put together a program that takes students from 0 to hero, if you like. And the problem is that it hasn't been done yet for science. Come back in a couple of decades, it might have been, but we can't hang around. So we've had to do it ourselves based on what is known already. The first step, of course, is the overall map of the territory. We don't want to be designing lessons until we know what are the critical understandings that students have to have after 5 years, which led us to think about big ideas. And that's because experts organize their knowledge around fundamental principles. They know the big things about their subject, and all the other knowledge connects to that. So the equivalent in science are these big ideas, not controversial. We've been talking about those for decades, really, but we've actually put them into practice, and we've gone down a level because a big idea is essentially a long-term quest to connect all your understanding together. What you need at each year level is a way to break it into a smaller piece, and these are the key concepts. This is, if you like, the building block of Blueprint, 100 key concepts, sequenced based on the research that we've accessed, and obviously principles like easier stuff first, more quantitative stuff later, and you end up with a progression. And we've divided it into 13 threads called these big ideas, and they have different topics, concepts and units every year. Students come back to them pretty regularly, and that's what allows them to build on previous concepts, and also what allows you to junk all that repetition, the idea that you do a topic in year 7 and you repeat it largely in year 9 with a bit extra because students have forgotten. You can look at our previous mastery courses where we've built on this idea that psychological research says that the greater the depth students learn things the first time, the less they have to relearn them. So mastery actually means building securely on a foundation of earlier ideas, and so you can keep progressing and not have to repeat from 0. So these concepts are the foundation. We organize them into small groups. The units are 2 or 3 concepts, and they are designed to take up about, should we say, about 4 lessons on average per concept. So it's about a few weeks per unit, depending on the size of the concepts. And they're all different. That's the point. There's no sort of double page spread, 10 topics per chapter, all of that stuff that's made up by publishers rather than educationalists. Apologies if you happen to be one. And then the curriculum gets decided by the publishing editor, and the emphasis that you put on things is basically random. We reject that completely. We've figured out what's important, and everything comes from knowing why we're doing these things. So it's well designed, but it actually does have to cover the curriculum. So Blueprint aims to cover combined science. It's modeled on AQA Trilogy, because AQA originally funded us to analyze their content, and everything that is in Trilogy Combined Science is in Blueprint. But it's not necessarily in the same order, because we've worked out a kind of developmental sequence. It's important that the curriculum is actually viable. So teaching in depth makes people scared, like I don't have enough time to do it this way. So we did work out estimates for each stage and each concept and each unit in each year. And we've made the whole thing fit within the years, within the 5 years. And to prove it, we've developed a course in year 7 and 8 that is actually teachable within the time. So I don't think there is any argument in our view that you can't teach in this desirable way purely because there's too much content. If you organize it in this rigorous way, it is possible. So what about if you're not doing AQA? Well, there's not much difference in the ideas between the 3 awarding bodies, because they're all based on the same criteria set by Ofqual. So actually it's a small job to match to the other syllabuses, and in a little while we may be supplying links so you can do that more easily. Similarly, for separate sciences, we haven't yet aimed at that, but we've scouted the territory, and we know that it's only adding a few topics here and there and some extra statements. So not difficult to adapt. We could have published Blueprint a year ago with just knowledge, scientific ideas, but we suddenly hit ourselves on the head realizing that enquiry hadn't been given proper visibility. It's actually on the same level as the science ideas in the assessment criteria. So really it needs to be programmed in. And that's why we spent a long time figuring out a strategy for getting inquiry in there. What we have is now 27 skills. All of them are taught in year 7 and 8 units, and they're all revisited many different times. So when you look at a planner, you'll see that for every idea, here's the idea of building blocks in the concept of cell structure. There's a matched inquiry skill, argue for a claim. And what we did was we tried to find natural partners between the ideas and the content to make sure everything was covered again and again. Gemma, I'll have a pause there. Have we got some questions? Ah, Gemma, are you there?
Sorry, I just got disconnected. I'm back. Let me just check. We had one about, find the chats again. We had one about, does everything in year 7 and 8 cover the Key Stage 3 national curriculum?
You can answer that.
Pretty much. I was just trying to think if we had any kind of odd statements in year 9 from the national curriculum. But I don't think, I'm not sure. Off the top of my head, I couldn't say 100% certain, or they are covered somewhere.
I think there will be some that are in year 9.
Yeah.
Because after all, the Key Stage 3 syllabus was designed originally as a 3-year program, not 2-year. But you would again have to do a little bit of adapting if you've been using that syllabus to move to our 5-year plan, because inevitably we've had to move things around to get this seamless progression over 5 years, and so we don't have to repeat topics that were done in year 7 again. So unfortunately there is some changing even from what we produced a few years ago. As our thinking has progressed, we found better ways to sequence the content. Okay, so let's get into the detail of the planners. They're based around this teaching model. It's not particularly complicated. Essentially, there are just 5 stages, we think, in going from, let's go to the next slide, from a novice in that particular concept to someone who's got more expertise. I hate to say that, you know, we're promising everyone to become an expert after that 1 week of teaching, but you get the idea. It's a progression. And there are these 5 steps we've set out because they're all essential. So the research behind each of these is pretty clear. You can't really start acquiring new knowledge until you have, if you like, activated and checked and reflected on what you already know. From the teacher's point of view, if we start teaching without knowing what students already know, we're likely to be, in some cases, going above their heads. They won't have that prior knowledge, or they'll have misconceptions which get ignored. So that activate stage is really about getting the foundations in place before you build on them. I think everyone nods and goes, yeah, that's fine, but we don't often do that enough. We do a quick review quiz and we think that's sufficient. But in fact, prior knowledge is one of the most important things in what students ultimately learn. So any investment in finding out and discussing and getting kids to articulate their current thinking is going to pay off. So acquire is fairly obvious, but we've put in a technical term, schema there, which is part of the expertise literature we talked about earlier. What it means is an organized body of information, rather than a set of facts that students might come away with. What we're talking about is that they have to have this key concept really well formed in their mind. And that's the key to going on with apply and analyze. So given that that schema is the really essential outcome of this unit, it makes sense to put the formative assessment in green straight after. You want to know after the teaching if students have got a good enough understanding. Because if they haven't, then going on to problem solving is likely to cause, difficulties if students don't already have enough of an idea. Because you're going to be going on to things which involve going beyond that. And so it really makes sense to focus on getting the acquire strongly understood. And if there are problems, you reveal them in the assess stage and you go back and you give students more opportunities to fix problems with their understanding before going on to the more advanced stuff. So apply and analyze are more difficult. And we focus really on teaching strategies so that students can do them better, rather than just giving them loads of questions to do, which will essentially sort them by ability. We want everybody to get better at doing that, in the same way that an English teacher would focus on, grammar or story structure or genre, whatever it is, to help the writing process develop. But in science, these things are much more kind of implicit. We don't have these ready-made strategies. So there's work to be done there, and that's the subject of a future webinar. I said there was a set of steps, and you'll see in the planners that we use this word goal. What we're saying is that each step has a goal. So in Activate, the student's goal is to show understanding before they go on to the new stuff. In Acquire, it is to construct, a mental representation of the main idea. In Apply, it's to use this understanding in a variety of contexts. And these goals, or missions, if you like, would show you the steps in students' progress along the way. We've defined the knowledge in the planner, but the goal, in a sense, is equally important. It's not just knowing that stuff, it's what they can do with it. So that's why there are these two dimensions in the planners, one for the knowledge and one for the goal for each stage. And if students can get through all those levels, obviously they've got a pretty good grasp and are likely to do well when they're assessed. And it may be that some of the students, especially earlier on in the 5 years, they don't get to these 5 steps all the time. And that doesn't matter, because what matters is that they build their understanding as deeply as they can. And over time, they'll find it easy to go further. Gemma, this I think is for you to tell us about.
Yeah, so this is an example of an Acquire activity that we created in our complete mastery materials for feeding relationships. So quite a lot of the time we saw in other curriculum materials, food webs was taught by just showing students a food web. And by doing that, they're not really building a very good in-depth knowledge of what a food web's actually showing. So we decided that this activity, which is based on the goal at the top there, we should get them to construct their own food webs. And it's also a literacy task, because on the right there, you can see a student sheet. They have quite a lot of text to read through and pick out the feeding relationships, form them into food chains, which they can already do because that's Key Stage 2 knowledge, and we would have activated that knowledge at the start in the Activate stage, and then join them together to create a food web. So doing that activity, they're actually building that knowledge themselves rather than the teacher just telling them this is what a food web is.
Would you like to describe this one?
Okay, well, this is a planner for our energy key concept. So this is what the planners will look like. They will show you the learning stages. We've only just shown you the top of this one, so you can see a bit more clearly. So we've got the Activate and the Acquire stage, and each stage has got a learning goal. So in the Activate, it's to show understanding of your prior ideas. And in the Acquire, we've got the goal there, which is what the activity is based around, like the one I've just showed you about food webs. And then also we've got the levelled knowledge, but I think you're going to talk about that separately, Tony.
That's right. So in this energy unit, it's divided into 3 parts, this Acquire, the knowledge acquisition stage. And that's because when we were planning it, we determined that there were probably 3 ideas that needed an extensive amount of time for students to grasp them. And so rather than just sort of rush through and treat it as content to be, communicated, we think students need to spend time getting some experience of and thinking about kinetic energy and relating energy to the speed or the mass of an object in terms of what it can do with that. And potential energy is a sort of separate lesson where students think in terms of what objects that have been raised up or stretched can do with that energy. And then A third component to the concept is the idea of conservation, when you have transfer of energy, knowing that it doesn't disappear or get created. So we've broken it down into these three parts because we think that's going to be sufficient to give students a secure grasp of the concept. And in general, each part is designed for about one lesson. With each part, there are various levels of knowledge, which we'll explain in a minute, but the key idea is the one in yellow. So here it is blown up. The main thing about kinetic energy students need to understand, we think, is that energy is quantifiable. We can keep track of it. And in kinetic energy, it depends on these two quantities, mass and speed. That's the main idea. That's really the focus of the main activities in that lesson. But of course, students need more knowledge than that. And so level 2 ideas support that main idea, the idea of an energy store and the idea that energy can shift from one store to another. But notice that they are, if you like, at a lower level, because that's not enough. We don't just want to give them an energy circus and say, you know, this wind-up clock does this transition and this one shows that transfer. That's kind of, you know, traditional approach, but they don't actually do more than learn a few labels. And the Institute of Physics has kind of debunked that whole approach with a much more thoughtful interpretation of what energy teaching could be. And that's what we've been driven by here. So the hierarchy of knowledge here is really telling you what they need to understand in more depth, what's the most important idea that students are going to have to understand so they can apply it, and telling you how long, therefore, you might want to spend in the classroom to give the students that sufficient grasp. And that should be helpful to planning lessons. And as you'll see, we want to avoid the kind of lessons that we see that are essentially just chunking up the content in the statements so that, you know, 10 minutes on this, 10 minutes on that. That kind of thing is what contributes to the sort of superficial knowledge many students develop. Okay, Gemma, we're going to get into the first two stages of the planner. We're going to cover these today, and we're going to leave the other stages to another webinar. Would you like to start?
Okay, so if we look at the activate stage first, Tony's already talked a little bit about this, but typically the activate activities that you would find in a published scheme of work would be a very quick starter activity at the start of a new topic. So, for example, this one here from a published scheme of work is a 5-minute activity. Students are just matching words with definitions. Some of these words they may have come across at Key Stage 2, others they probably haven't. So, you know, it's really important that these kinds of activities are designed around finding out what students already know, highlighting any misconceptions they may have in order for you to confidently move on to the next stage of acquire, knowing what they already know, so you can build on that. So that's basically what the activate stage is for then. It's assessing that prior understanding before you teach a new concept. And it's worth spending quite a bit of time on. So in our materials, we've put aside half a lesson for this. And this is the kind of activate activity we've come up with. We call it a pre-assessment. So this is from our complete mastery materials for feeding relationships. So before they go on to acquire that new concept of food webs, we're getting them to activate what they already know about food chains. So they should have done food chains at Key Stage 2. And we know they should have been introduced to producer, predator, and prey as keywords, and they're the only ones they probably understand. So this activity, we give them these little boxes of what eats what, and we asked them to, can you construct as many food chains as you can for this habitat of a field? And there's other habitats on the sheet as well. So they're really activating that knowledge and using what they already know. And if they haven't done food chains at Key Stage 2, and if they don't know what these words mean, then that signifies that you need to spend a little bit of time going through those things before they're ready to move on to food webs. So just a little bit of time here for you to think and put any comments on the chat about a concept that you taught when you were at school. Did you actually use a kind of activate task at the start of the topic? How did you design that? And did you find, if you did use it, how did it help you when you went on to the new learning? So just put down anything you want to do in the chat about that.
Okay, I think we should move on as we've got one more section to cover. Yes, Gemma?
Yep. Do you want to do the start of the next one?
Okay, so now we're going to go on to the other stage we'll talk about today. If you like, the main stage. We've had some questions about this. This is really where one of the biggest differences is in the depth that we go into the teaching of the content. So we have to make a sort of contrast here so the difference is clear. So we're just, for argument's sake, this could be a publisher's lesson plan outlined for part of the forces unit. What you might see is there's a few lessons and they're broadly just topics and they end up with a practical. If we focus in on one lesson, and this is built on a real example, you get a bit of introduction and then you get straight into the concept. And essentially, the approach is to try and make that concept as simple and obvious as possible so that you can just put it onto a PowerPoint slide, explain it, get kids to look at some examples, classify them, and job done, right? So that kind of approach assumes that students can grasp these things with basic direct instruction. In our previous webinars and for 2 or 3 years, we've been arguing that that's fine for simple stuff. It's fine for skills. But when it comes to difficult scientific ideas, there's about 30 or 40 years of research and all the misconceptions literature that suggests that it isn't sufficient. Because scientific ideas are complex, they're all connected, they're hierarchical, and students often don't come in with the kind of background knowledge, or they come in with ideas that would block them being able to understand the new ideas. And if you don't take account of that, and if you don't give them sufficient experience and help them to model these new complicated theoretical ideas, they're unlikely to come away with the more than the superficial understanding. And we've called that carrot gate in the past. That's the kind of thing where examiners just switch the context slightly and students have no idea what they're talking about. And we think that is a direct result of this kind of PowerPoint pedagogy. As I say, it works for the simpler stuff, but science has these complicated ideas. And we actually changed Blueprint an awful lot after doing the original CPD, because when we put out the first version and we said to teachers, how would you then create a lesson on this? What they came up with was still very similar to that. So we thought, well, we haven't gone far enough. We haven't really described exactly what we mean. And that's what led to this levels and the idea of progression and building on stuff they've done before, and really being systematic about how we develop this expert understanding. Gemma, I think this is one of your slides.
Yeah, so I'm going to talk a bit about chemistry now. We've done biology, we've done physics, let's do some chemistry. So this is one of our Year 8 chemistry key concepts called acid reactions. And this diagram really just shows you how it fits into the big idea, which is reactions rearrange matter. So you can see that it builds on Year 7 from chemical and physical and neutralization. And it's important for students when they get to Year 11 as well, making salts, that you need to understand acid reactions. So that's how it fits in. And we make sure that all of our units are in a logical progression in that order. And we show you the links on the planners as well. So what units they should have done before. So here is part of the planner then for acid reactions. This is the enquiry, called chemical reaction. So you can see there that we've split it up, the information up into 3 levels, and the levels are showing you time priority, so where you need to spend more or less time. So we've got level 1 where you don't spend very much time at all, it's just facts, things to understand. And then at level 3, that's where the deep understanding really needs to come into it. There's where you need to spend plenty of time for students really to understand that. So that's the conceptual understanding that goes alongside this. So if we look at that level 3 idea in a bit more detail, it's chemical reaction. So atoms in the reactants rearrange to form the product, and a word equation summarizes the change. So even though this key concept is teaching acid reactions, the actual level 3 understanding that we're really focusing on is all about what is actually happening during a chemical reaction. So in Year 7, in that chemical physical key concept, they observe chemical reactions, but they don't really understand what is going on for that new product to be formed. So in this key concept, we're going to focus on when you do a chemical reaction, where does that new substance come from? How does it get formed from the reactants? And they're going to start modeling this using diagrams like the one shown on the slide there, to figure out how the products are formed from the reactants. And that is a really important skill in chemistry. If they don't understand that, they're not going to be able to progress much further on in chemistry. So that's why we're focusing the majority of our time on that idea. Of course, this unit's got, or this key concept, has got other ideas that are important, and they are important to understanding acid reactions, but we're going to spend less time on them. So that's gas tests. So they're going to learn about 3 different gas tests. They're going to carry them out. They're going to learn about acid carbonate reactions. So very simply, if an acid reacts with carbonate, what do you get? And they're going to be able to learn the skill write a word equation. And then level 1 ideas, these are the facts, these are the things you're not going to spend very much time on. They're going to understand what a reactant is, what a product is, salt type. So by that we mean that hydrochloric acid forms chlorides, and a carbonate. So what actually is a carbonate? Well, it's a compound with carbon and oxygen in it, and that's important, obviously, where the carbon dioxide comes from. So also in our planners, we highlight skills. So for every key concept, we choose a skill that we think is important when teaching the main idea, and you can incorporate into your activity. So for this one, it's all about modelling, using relevant features and behaviours of a model to account for aspects of a real phenomenon. So it's using that model of particle arrangement to figure out what's going on in a chemical reaction. And then we also sometimes, if it's a practical lesson, we're including techniques. So as I said, in this lesson, they're going to be carrying out reactions. They're going to be adding acids to carbonates. They're going to be observing what happens. So they're going to be observing, oh, there's bubbling. That must mean the gas is being made. They're going to be doing gas tests, and they're going to be using chemicals safely. So there's lots of practical techniques as well in some of the lessons that they're going to be practicing. And all 3 of these, they were introduced in Year 7. So they're just practicing them again in Year 8. So the goal, we touched on this a little bit when I talked about the food webs lesson. So the goal is the activity that the students are actually going to carry out in order to build up that main idea, that understanding. So in this activity, they are given a range of carbonates and a range of different liquids. Some of them are acids. They add each liquid to the carbonate, and then they're looking for patterns. So that's another really useful skill they're doing. They're spotting that, oh, when an acid reacts with a carbonate, we get bubbles. And they know from year 7 that bubbles means that a gas is forming. Then they learn the gas test, so they're testing that gas. They find out it's carbon dioxide. So now they've got these 2 pieces of information. They've got a particle diagram of what a carbonate is, and they know carbon dioxide's formed, and they know what particles are in carbon dioxide. So they're thinking, where does that carbon dioxide come from? They're building up that understanding that the atoms in the reactants must have been rearranged to make that carbon dioxide. Then they can also figure out what other 2 products are formed as well. So the salt and the water, and where they came from. So it's all about building up the understanding about particle rearrangement. Okay, so again, just a little bit of time for you to put any comments or any questions in the chat about, are the activities that you're planning in your lessons really helping to build that understanding? Are you thinking about what the main ideas are that you want to focus on in your lessons as well?